Hi, everyone. Can you hear me with my mic? Okay, great. I'd like to thank Nick and Connie for inviting me. I was last year at New York's event, and that was the first time I attended MLconf, and it was very much fun, and I'm happy to be back here again. So I'll be talking about, sorry, let me first make that full screen. So I'm a faculty at UC Irvine, and for the past few years, I've been looking at tensor factorization techniques for training a range of different probabilistic models, and the most recent work we are excited about is how to use that for feature learning and for training neural networks using alternative methods compared to the popular backpropagation methods. So, not sure why the pointer is not working. Okay, let me just use it here. So, we are aware of data deluge in a number of different domains. We have social network data, genetic data, image data, speech data, and it's growing in huge amounts, right? But data is always not useful information. I mean, the challenge with big data is it's highly messy. There can be so many different sources of corruptions. There can be outliers, missing information, and so on. So that's what makes the problem of data deluge challenging, in that the information we want to extract from it is literally a needle in the haystack. And this is what calls for sophisticated techniques to find this useful information, right? So we'd like to come up with fundamental principles of how to model this useful information in this high-dimensional, large-scale data, and what are the algorithmic approaches to extract it efficiently. So this is where matrices and tensors come in. I'm sure all of you here have used matrices, right? Matrices can be used to represent vector data. If I have many different columns of vectors, I can think of that as a matrix. But on the other hand, for tensors, you can think of data that's much richer. So data these days can come from different sources, can have like multiple different relationships. And to model such rich data, we need tensors. So you can essentially think tensors as higher dimensional extensions of matrices, right? So matrices are two-dimensional arrays, whereas here a cube is a three-dimensional array. And so we can now represent higher-order relationships with tensors. So for instance, with a matrix, we've all used that to capture covariances or correlations in data, whereas now with tensors, we can capture higher-order relationships. For instance, it could be third-order moments in data or higher-order ones. And so this is where tensors can be useful in a much wider context compared to matrices. If we want this general framework that takes like all these matrix computations to also these higher order arrays. So the popular matrix computation that we are all aware of is spectral decomposition. Right? The task is to decompose a matrix into sum of rank 1 components. This is popularly known as PCA if we do this decomposition on covariance matrix of data. And the idea is with PCA, we can get a low-dimensional projection of our data. Right? So we can find a subspace that fits the data points efficiently, and by doing this, we can hope to reduce out-of-subspace noise, and as well as reduce the computational complexity of our problems, because we are working on lower dimensional data by doing this reduction. So this is the popular technique of SVD for matrices, and indeed there are a lot of highly optimized linear algebra libraries to do this. And we can ask the same question with tensors to ask that, if I have a very large tensor, so think of a tensor that could have like a million by million by million features or even more, right? So if you try to just operate on this large tensor, then it's not feasible. So we want, again, to find low-dimensional representations of these large tensor structures and then use that to mine the useful information in data. So I'll talk a little bit later on how doing these low-rank representations of these observed tensors can reveal hidden patterns in data. But the algorithmic question is, given I have a tensor, what is the equivalent of this SVD for matrices, right? So we can ask the same question, can I find a low-rank efficient representation of my input tensor into some of rank 1 components? So how to solve this problem indeed becomes harder than the case of matrices. So with matrix, we know, theoretically we know we have the guarantees that we will get the right decomposition, and we have efficient parallelized techniques to solve for this decomposition. But with tensors, the algebra is much more involved. In fact, there can be tensors where this is a NP-hard problem to solve. And what we've been looking at are scenarios where we can show that this, in fact, is a tractable decomposition. So we've developed efficient techniques that, in fact, have very similar computational complexity as the matrix setting. So even by going to higher order tensors, we are still not losing the parallelizability and the scalability of the matrix methods. So in a way, this is like the best of both worlds, because we are extending matrices to these higher dimensional or higher order structures, and at the same time, we are retaining the computational efficiency of matrix-based methods. So those are algorithmic approaches we've been working on. So I won't give all the details of those approaches, but the main idea is they involve efficient use of already optimized linear algebra libraries. So we need some simple computational techniques like SVD, some matrix and vector products, and that's mostly it. So it's a very few lines of code, and we have some implementations on our website. You can check it out. That will solve these tensor decomposition problems. And now we can, and these are also parallelized operations. So we have a cloud-based implementation. We have one on Apache Reef from Microsoft that my student interned at Microsoft Redmond last year, and we have that in the open sourcing process. We also have a Spark-based implementation that we are currently testing, so we hope to release that soon as well. So we have a number of implementations that can exploit the parallelism of cloud-based systems, and that makes these methods much faster than other techniques for training probabilistic models. So I'll show you some comparisons where we get even up to 2 or 3 orders of magnitude improvement in running times compared to likelihood-based techniques that are the most common norm for training probabilistic models. And these methods are also naturally suited for GPU systems. Again, we have very optimized linear algebra libraries for GPUs. We can also exploit those to take care of now tensor computation problems as well. And just this plot here shows some scaling for the tensor method we ran, and with optimized code on GPUs, like using device-level interface, we could get much better speed-ups than running it on CPUs. So, with tensor methods, the idea is we can mine much more useful information. We can go beyond matrix computations, but at the same time, we can exploit all the existing optimized code, linear algebra code, both in GPU, CPU, and cloud-based systems. And so that's why I argue this is kind of the best of both worlds in terms of having now more probabilistic modeling, but at the same time having the simplicity of matrix methods. So I gave a recent talk at Strata in San Jose. I'm not sure any of you were there. And Ben Lorica, who's at O'Reilly Media, who invited me, he wrote an article to call for more developers for developing, open source tensor libraries. And I'm, very much interested in pushing that forward and having a much more, accessible code bases and implementations for wider use. So if you're interested in that, I'd be very happy to work with you on that. So please come and see me after this talk. So now that I've briefly talked about the ability to manipulate tensors efficiently and to find low-rank decompositions of tensors efficiently, let's see where they are useful, right? So why do tensors, or what kind of tensors do we even capture from data? I mean, in cases when the data itself is of a tensor structure, it is natural. Then we can, look at the data and then we find this low-rank approximations. But in many other settings, the data may be much simpler. The data may be just a bunch of vectors. Those are the samples. Then where do tensors come in? So what we'll see is we can use tensors to capture higher-order moments or higher-order relationships among the different data dimensions. And by implicitly manipulating those tensors, we can learn a range of probabilistic models. So in fact, in many of these applications that I'll show you, we don't even have to form the tensors explicitly. We can implicitly manipulate them, so we don't need huge storage requirements that would have been necessary if we had to form these tensors. And that's the power of these methods, that we can do them online and we can do them without storing huge tensor objects. So when it comes to different latent, probabilistic models, having latent variables is very crucial for modeling. Because whatever effects you account for, there may be always some additional hidden effects that are not captured by all the covariates or the observed variables that you have at hand. And since you do not have labeled information in most cases for this is the setting of unsupervised learning. So you do not have information about these hidden variables during the training process. And we can think of these hidden variables as also capturing the useful hidden patterns that you'd like to extract from data. And that's and there's indeed a huge amount of work on probabilistic modeling, starting from basic mixture models where you want to think of data as belonging to different exclusive groups, right? So here there is a cluster that's like of red points and the green points, and it's fairly visually easy to see that these are coming from different groups. But you can, of course, come up with much more sophisticated probabilistic models where there is no such clearly separated clusters. So you could think of now data belonging to multiple groups. I mean, these are called mixed membership models, where just clustering-based techniques would not be able to separate them. So that's where probabilistic models are a much more sophisticated means to model the input data compared to clustering methods, which only try to separate the points, right? So it could be like a lot of hierarchical relationships, like a huge set of different hidden variables that have various relationships and are also related to observed variables. So we can posit all these sophisticated probabilistic models, but the challenge in general is how to learn them efficiently. Because the usual norm for learning is to maximize likelihood, right? So I have a model, if this is the candidate model for my data, I'd like to ask, find me the best solution that fits the data. But unfortunately, the problem is highly non-convex. So when you have hidden variables, this leads to expectation maximization or some form of local search on this likelihood objective, which is non-convex. So just if you try to visualize it, there are lots of ridges and valleys, right? There are so many different local optima, and this problem only grows as you have more and more dimensions. So as you have like more large-scale data, the problem becomes computationally infeasible. And this is the computational challenge with big data, because as we have more data, the optimization problem also becomes harder. And so this is the problem that, that's why you need a lot of tuning in practice. You need like kind of very clever initializations to make it work well in practice in these techniques. But what we wanted to ask was, are there alternative methods to train for these probabilistic models that have some fundamental basis, that we can say that under some conditions, we'll actually succeed in recovering the correct parameters that will actually converge to the global optimum, right? So what we've shown is for a range of different latent variable models, in fact, tensor methods are consistent. They actually yield the right parameters of the model if the data is in fact generated from that models with some, and you can also handle some amount of perturbation away from those models. So as examples, the basic Gaussian mixture models, we can train using these tensor methods where we look at third-order moments in data. So essentially, you look at, if you look at pairwise moments, those are correlations. The third-order moments now becomes a third-order tensor, and what we show is decomposing that tensor and finding low-rank representation of the tensor, where the rank is equal to the number of components, will yield the correct model. So you can actually get the correct parameters of the model by using the tensor method. Whereas running just EM or any of the other approaches will not have any such guarantees, and you may not get the correct fit for the mixture model. And in fact, that's one of the challenges when people say that in practice, these probabilistic models, these sophisticated models are not working. It's not clear if it's because the model is bad or the optimization is bad, right? So it's not clear you've actually gotten a good fit for the proposed model in many of the settings. Whereas with tensor methods, we have a firm theory that says under some natural set of conditions that seem natural in a number of settings, we can guarantee that we can get to the consistent solution for these models. And there's a number of other popular models that can also be learned using this tensor methodology. So if you think of hidden Markov models, that's very popular for modeling temporal sequences. So there are these hidden factors that evolve over time, and then they generate the observed data. So again, you can think of the tensor as looking at consecutive measurements in data, right? So if you only look at 2 consecutive measurements, that's correlation, and that's a matrix. If you look at 3 consecutive measurements, that's a third-order tensor. And what we show is finding low-rank representations of these tensors can correctly yield the parameters. And similarly, there are so many other models, such as independent components, which are popular for blind source separation. So for instance, if there are many audio speakers that are speaking at the same time, you don't know what the sources are, and you don't know how they mix together. So you can learn both the hidden sources and their mixing through these models. And there are a lot of topic models. The latent Dirichlet allocation is popular model where there are multiple topics that can appear in a document. And we've shown that, again, by looking at co-occurrence counts in data, meaning that you look at 3 words in every document, what are their counts, and do it for every triplet of words, we get a third-order tensor. By decomposing that tensor, again, we can get the correct LDA model from tensor methods. And indeed, our framework is very general. You could think of other multi-view data as well. There could be different sources such as audio, video, text, that all kind of relate to the same hidden factors that you'd like to learn. And we can incorporate these different sources. And by looking at the cross relations between these different sources of data and decomposing them, we can find these hidden factors. So it's kind of the overall framework is, for learning these probabilistic models with hidden variables, we have sources of unlabeled data, right? So in this setting, we may not have labels. For instance, in the social network setting, we may not know what communities people belong to. In text documents, we don't have labels of what the underlying topics are. So in this challenging setting where we don't have any labels, we can posit many probabilistic models. But the methodology is common, that we form moments which look at these higher order relationships in data, and by decomposing it, we can find the actual models. So for instance, in the social network setting, we can find inferences of how people belong to different communities, right? And in fact, each person can belong to multiple communities here. And these are called mixed membership models, so we can capture all these multiple attributes of every person through their memberships into different communities. And with text documents, we can mine for all the topics that are present in various documents. So one comment I'd like to make here is, tensors are in fact crucial to learn these models. So if you just looked at matrices, meaning you just looked at pairwise correlations in these different settings, they will not give you the full model parameters. Right? Because I'm sure all of you here are aware of matrix factorization techniques for recommender systems and other setups. But that doesn't yield a full probabilistic model because you get these latent factors up to rotation. Because of the SVD, you only get an orthogonal representation. But with tensors, the algebra is much richer. In fact, you can find a tensor where the components need not be orthogonal to one another. And you can also find tensors where the number of components could be even larger than the dimension, meaning the rank of the tensor can be even higher than the dimension. So these are so-called overcomplete models, and I'll show a bit later that for feature engineering, you'd like to kind of capture and extract as many features as possible. So this is where tensors can go much beyond matrices. In that, they are capturing much more information. And what we show is through their algebraic structure, they actually can learn the parameters of these many different latent variable models, whereas with just matrices, we would not be able to fully capture the parameters. So that's why I argue that fundamentally, in all these applications, tensors are crucial, and the matrix methods, they may reveal some information, but they're not revealing the entirety of information in these different applications. So let me show some simple demos to kind of drive home the point of what I'm saying about these different latent variable models. So here it's a simple Gaussian mixture model. So you see here there are two components here. There's the red and the green, and there are no labels. So this is the unsupervised setting. We don't have any labels when we train the model. And these are the true mean vectors. So the red and the green lines here are the true vectors. And we want to see if the tensor method actually correctly learns these two mean vectors as it goes through the iterations. And on the left-hand side here is the heat map of the error tensor, meaning we have the tensor that's computed from the observed moments, the third-order moments of the data, and then we are trying to fit it to a low-rank representation. In this case, since it's two-dimensional and two components, it's a rank 2 representation of this tensor. And you can see that in the beginning, there is still some error because, the more blue it is, the error goes down. And we want to show the point I want to make here is as the error in fitting the tensor goes down, you can also see on the right that, the vectors will become more aligned to the true underlying, ground truth of these mean vectors. And that's what you see here, that it's gonna now, because this is just two-dimensional, this is actually quite fast, that it converged to the true mean vectors. And this is perhaps not surprising because it looks like an easy case, right? There are these two clusters that are fairly well separated. But now let's make the problem harder, and let's increase the variance of these two different clusters. In this case, you can see now that there's almost like, the clustering methods would definitely fail here. In the earlier case, you could have tried to separate them using clustering methods and then use that to learn the underlying model. But now, if the variance is too large and there's no separation in the clusters, you cannot use clustering-based mechanisms. But what we'll see is, instead looking of these tensor moments, in fact, we can get convergence very quickly, in fact, to the true components. So that's the power of these methods, that they're not relying on separability in data, but they are looking at the relationships, these higher-order relationships in data, and therefore can still learn in challenging settings where other methods can fail. So this was a simple example to show that we can learn, for instance, Gaussian mixtures with these tensor methods. Another example that I'd like to show is for text data. So I'm not sure if the font size is visible enough to completely see, but the idea is, I mean, these ended up after running the tensor method for just, I think, about a few thousand iterations, which ran under like a minute in a single workstation. What we saw was these were the actual words recovered into different topics. So you can see here, this is about economy, this is about children and reading, this is about games. So there's like, topics that we just listed them. And I wanted to show here, as we run the method, during different iterations, it quickly like kind of finds these words to be exclusively into these different topics. It's just a bit slow in the beginning because I think of the. So this is just like, I mean, red means here it is converging. So you can see that many topics have converged very quickly, and we've just slowed this down for visualization because in practice this is very fast. So you can see that you can get very quick results in terms of convergence for these tensor methods, and you get access, you can see that these topics are very interpretable, and at least in this simple case, we can learn them with tensor methods. So we also ran this on, ELP data, and DBLP was the co-authorship data. So there what we did was we looked at businesses and just asked, who are the common users who rated the different businesses. So we didn't even take the review text into account. So this was a very simple, just the basic information of how did people co-rate or co-review different businesses. And using that, can we learn what the underlying business attributes are. Right? And because in this case, we have the business ground truth attributes, we wanted to see how well they are captured. So what we saw was we recovered indeed restaurant category, which is dominant in on Yelp, but also we recovered small business categories such as hobby shops and mass media. And the intuition is these tensor methods are capturing information of who are the users who co-review them. And so if you think about hobby shops, people are usually very dedicated towards them, right? So they may review many different hobby shops once they are into that. And that's what these tensor methods will capture, because they're capturing like how are people co-reviewing these multiple businesses. And that's why it could work very well in practice, even when the probabilistic model by itself may not have a very good fit in some settings. And as I said, we can learn rich probabilistic models where there can be multiple memberships for every node. So instead of classical community detection works, which try to classify each node into just one community or one group, we can now have multiple communities for every person. And so for instance here, from our method could detect that a business is also a restaurant, it's a bar, it's location. So you can capture multiple attributes in an unsupervised way by running these tensor methods on these various kinds of data. And just to show some running time comparisons, we have the more extensive times in our papers. But the state-of-art method for training these models has been these variational methods. And in fact, there's stochastic variational methods that have been well optimized. And we see that huge difference in running time in up to 2 orders or more orders of magnitude improvement with our methods. Because if you think about trying to optimize likelihood in this huge space of models, especially if you think about graph, the graph can have up to n square edges if n is the number of nodes. So this is a high, very large parameter space, and likelihood-based methods, are very slow, and even each update of these likelihood-based methods are very expensive and hard to parallelize. for these models. On the other hand, the tensor methods have all the advantages of basic linear algebra techniques, basic matrix factorization techniques, and yet can yield now richer probabilistic information through the models. And we have even extensions to doing hierarchical tensors, and we've run it for healthcare data sets efficiently. And the one most recent one that I'll just give a very quick pointer, because this is the work we're very excited about, is to use these tensor methods to train neural networks and for finding good features. So the idea is, till now I talked about the generative setting where we have data, we want to fit it to some hidden variables. But in the classification setting, we have labels, we have data, and we want to find good feature representations of it. And what we've shown is by using so-called score functions, which capture local variations in data, and then correlating them with the label, we can find good classifiers and use them as weights for neural networks. So just very quickly, I'll show the demo, and I'll be done after this. So in this demo, what we see here is there are, in this green cluster is -1 label, and this is the +1 label. And by running the tensor method, in fact, you can, correctly classify the clusters as well. And you can see that the tensor method also has good residual error in that case. So we can find the weights of the neural network efficiently. And even when the clusters become less separated and more mixed, even in that case, what we see is that our tensor method, in this simple example, can recover the neural network that separates them well. And so kind of the idea is, in order to find good candidates for weights of a neural network, we can use these tensor moments, and by decomposing them efficiently, we can find them. And we are now running extensive experiments to see how they compare to backpropagation, and we're seeing that these methods can yield much better candidates for neural networks. Thank you. I'll stop here.
Thank you very much. I see people are getting hungry, but I'll ask you to kind of wait a little bit for our last speaker before lunch.